My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have an understanding of how a computer adds floating point numbers stored in single precision, 32 bits. Enjoy! Before you begin this video, you need to have an understanding of how a computer represents a floating point number, and there is a separate video on this topic. Let's look at how we add floating point numbers in our normal base 10. Here we've got an example, and we're looking to add 5e plus 2. Now 5e plus 2 is a way of writing 5 by 10 to the power of 2. And we're adding it to 7 by 10 to the power of 2. Now the first thing to note is that you can only add these numbers if the exponents are the same. Now the exponents are the powers that are here, and these two powers are the same, or they're these numbers here. They are the same, so you can add them directly. And what we do is we add the significance. The significance are these numbers here. So if we add these two numbers here, we get 7 plus 5 is 12. So it's 12 by 10 to the power of 2 is the answer. And if we rewrite that in our scientific notation, that's equal to 1.2 by 10 to the power of 3. Now that worked out all nice and neatly, but what if we wanted to add two numbers with different exponents? So what this example looks at is that we've got 1.2232 by 10 to the power of 3, and we're adding it to 4.211 by 10 to the power of 5. Now the first thing to note here is that the exponents are different. And if the exponents are different, then we can't add it directly. So what do we do? So step 1 here outlines what we do. We normalize to the higher exponent. How we do that is we find the difference between the exponents. It's 2, it's just 5 minus 3. And we shift the smaller number right by that amount. So what we get is that 1.2232 by 10 to the power of 3 is the same thing as 0.012232 by 10 to the power of 5. Now what that has done is that it has turned this exponent from a 3 into a 5, and so now we're in a position that we can add the exponents, and that's what step 2 is doing. The exponents are the same, so we add the significance, and that's done for you here. Again, if I was to write it down, it would be 4.211. Now this is by 10 to the power of 5, and then the next one is 0.012232 by 10 to the power of 5 also. The exponents are exactly the same, so we can add the two significance, this number to this number, and what we get is written there is 4.223232 by 10 to the power of 5. And that's how we add the two numbers. Now the computer uses a similar method to add its two floating point numbers which are stored in 32-bit binary. So let's have a look at that. Let's try this example. It says that the 32-bit floating point number representations of A and B are as follows. So A, which I'll underline here, is represented by them 32 bits, and B, which I'll underline here, is represented by these 32 bits. And what you're asked to do is to find the 32-bit computer representation or floating point number representation of A plus B. Right, so you're going to look to see how the computer adds the two numbers together and then stores the result. Now if you recall from the last video, when the computer stores floating point numbers in 32 bits, there are three distinct parts. The first is the first bit here, which is the sign bit, and 0 indicates that it's a positive number. The next 8 bits store the exponent. Right, so I'll block these off. And the last 23 bits here store the significand of the number. So I've written them in for you. The first bit is the sign, The next 8 bits is the exponent, and the last 23 bits is the significant. Now, as you can see from this, let me write this down, both of these numbers, both A and B, are positive numbers because there's a 0 in the first position. And all my examples are going to be of the case where A and B are positive. Now, if we take a look at the exponents of A and B, the exponent of A, right, the exponent of A, right, is the next 8 bits. So it's 1, 1, 0, 1, 0, 1, 1, 1. And if you look at the exponent of B, the exponent of A and the exponent of B are actually exactly the same. So they're similar. So that's equal to that, which is equal to that. So they have similar exponents. If I was to convert this binary number here to decimal, I discover that the number is 215. You can do that directly on your calculator. Now, because the exponents are the same, to get the answer for A plus B, all I do is I add the two significants. Now, if you recall from the last video how the significant is stored, the significant always has a leading 1, and the computer doesn't store this leading 1, but it's presumed to be there. So let me write down the number A that is being stored by the computer in binary form. It's going to be 1 point, and then we write down the 23 bits of the significant. So it's 111, 0011, 1010, 4 zeros, 1100, and lastly 0011. And likewise for B, there's a leading 1 understood, and when we write down 000, 1110, 0101, 4 ones, 0001, and lastly 1100. Now remember that both of these numbers are multiplied by 2 to the power of 215. Now 215 isn't exact, we should really subtract 127 from it if you remember how that was stored. But the important point is that the exponent, the 215, is the same for both numbers. So what we do is we can just add directly these two numbers because the exponents are the same. So if we set about adding it, we'll get 0 and 1 is 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 and 1 is 2, so you put down 0, carry 1, 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 and 1, carry 1. So that's what we get. And remember that this number is by 2 to the power of 215. Now let me move the page down just to finish off this example. Now this is our solution for A plus B, right? But the computer can't store it in this form. Remember, the computer wants to store it in the form of 1 point. So we're going to have to move the fractional point here, and that's going to have an effect on this value here, the exponent. So if I write that down, it's 1.100, right? So if I just write the first 3 digits, then the next 4 is 0000. The next 4 is 1111. The next 4 is again 1111. The next 4 is 1110, and the last 4 is 1111. So what happens this 1 here at the end? Well, basically it gets lost and the computer runs out of space to store numbers, and basically this 1 is not stored. So this here now becomes by 2 to the power of, well, if you move the fractional point, it's 2 to the power of 1, and if I add 1 to 215, I'll get 216. So if I put a box around, the computer only stores, it doesn't store the leading 1. So this here is now going to be my significant. All right. And this 216 is going to be my exponent, and obviously I have to have it in binary, so I have to convert it to binary. You can do it in the calculator, or you can just add 1 to the binary number above, and what you get is, you get 1101, and then it'll be 1000. So if we write out now exactly what the computer stores for A plus B, right? So it's going to be 32 bits, right? Single precision. And what it stores for A plus B is, firstly, it's a positive number, so it puts 0 in the first place. Then it writes down the 8 bits for the exponent, so it'll be 1101, 1000. And lastly then, it'll write down the exponent, and that's, or the significant, sorry, and that is 100, 0000, 1111, 1111, 1110, and lastly 1111 again. Alright, so that's the answer to our question. Let's look at the next example, similar to the last but slightly more difficult. It says the 32-bit floating point number representation of A and B are as follows. So again, here's A, and this is how the computer represents A, and this is B, and this is how the computer represents B. And it asks you to find the 32-bit floating point representation of A plus B, just like we did before. So if we look at A and B, the first digit is 0 for both, so that means that both numbers are positive numbers, right? If we look at the next block of 8 digits, that gives us the exponents. And the first thing we notice is that the exponents are different. They're not similar as in the last example. So the exponent of A is this, and if we convert this into decimal, what we'll get is it has the value of 215. Just do that in your calculator. If we convert the exponent of B, which is this, to decimal, what we'll get is that it's 209. Now, the main difference is that the two exponents are different. So what we do is that we normalize to the higher exponent, and the higher exponent is 215. So normalize to the higher exponent, which is 215. If we look at the difference between the two exponents, the difference, I suppose I should write that down, difference between them, the difference is equal to 215 minus 209, which is equal to 6. So we're going to normalize the exponent of B, which is the smaller exponent, up to 215. So it's going to involve shifting B right by 6 places. So if we write down the significant of B, remember there's always a leading one, so it's 1 point. So the significant, I'll put a box around the significant here that I'm going to write down. It's 1.000, where am I? 1110, 0101, 1111, 0001, 1100. So that's the number that's stored. And remember that it's multiplied by 2 to the power of, here it's 209. So if we're going to normalize to the higher exponent, which is 215, let me move the page up so that I get a little bit more room. So what we're going to do, we're not going to change the size of B, but we're going to rewrite it with a new exponent of by 2 to the power of 215. And if we're going to do that, we're going to have to shift all the values in B to the right by 5 places. So our new B, right, is going to become 0 point, and you're going to end up with 5 zeros beginning 1, 2, 3, 4, 5. And then we're going to start rewriting B from the very start, writing all the digits as they occur. So the first digit is a 1, then the next next digit is a 0. So if I maybe block them off like this to show you what I'm doing, and the next 4 digits are 0, 0, 1, 1. The next 4 digits are here, 1, 0, 0, 1. The next 4 digits are here, 0, 1, 1, 1. And then the last 4 digits are here, it's going to be 1, 1, 0, 0. So again, what happens this block of 6 digits at the end? Well, the information just gets lost by the computer because it has no place to store it. So it now B is now essentially this number here. So now let's look at A plus B. A plus B is the same as B plus A, so it'll just save me writing it down again. So I'm going to put A under B, and A is in its original form, taking it from, remember, the leading one, and then writing down the significant as it occurred. It's 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1. And again, that's by 2 to the power of 215. Now the exponents are identical, so now what I can do is I can just add them two numbers exactly, and I'll get the exponents as being 215, the same as before. So when I add them, I get 1 and 0 is 1, 1 and 0 is 1, 0 and 1, 1, 1, 1, 1, 0, carry 1, 0, carry 1, 0, carry 1, 1, 0, 1, 1, 0, carry 1, 1, 1, 1, 0, carry 1, 1, 0, and then I've got 1, 1, 1.1. So that's my answer for, sorry, I'm running out of space, A plus B. Okay. Now this is the exact form that the computer likes to store the number. It's 1 point, so I don't have to make any changes like I did in the last example. This part here is going to form my significant, and this part here is going to be my exponent. So my exponent is going to be the same as it was for A. So if I look at A plus B, the 32 bits that the computer stores now for the answer is going to be, well, 0, because it's a positive number, right? Then it's going to have the exponent, and remember 215 in binary was 1101, 0111, so that's the exponent, that's the 215. And lastly, the significant, here it is here, I'll just extend that arrow, and you'll get that it's 111, 0101, 1101, 1010, 0011, and lastly 1111. So that's the solution to our question, the 32 bits that the computer has for representing A plus B. Now what I'd like you to do is to pause the video and take out a pen and paper and try these two exercises for me. They're exactly the same as the two examples that I have just done. And when you're finished, then turn back on the video and I'll go through the solutions for you. Okay, let's look at the solution for exercise 1. So the first thing is, well, both of them are positive numbers. The exponent values you should have highlighted, and I'm going to put a box around them here just to show you what they are. If you convert them to decimal, what you should get is the first one is 215 and the second one is 17, right? So the exponents are not the same, so you go about normalizing them, and you normalize them to the higher exponent, right? If you look at the difference between the two exponents, the difference between the two exponents is equal to 215 minus the 17, and that value turns out to be 198. So there's a very big difference between exponents. What that means is that A is in fact a very large number in relation to B, which is a very small number, right? Now, you should have in your mind what happens when you go to add a very large to a very small number. The very small number, in fact, has very little makes very little difference to the large number, and in some cases makes no difference when you're using a machine, i.e. a calculator or a computer. This is going to be the case here. If we look at B, right, and we write down the significant, and remember with putting in the leading one, it's 1.100, 1100, 0101, 0111, 1101, 1, 1, 0, 0. So that's b. And remember that it's multiplied by 2 to the power of 17. We want to rewrite it so that it's multiplied by 2 to the power of 215, right? So that the two exponents are the same and then we can add them. So what essentially are we going to do when we rewrite b? We're going to shift all these places here to the right by 198 places. But when we do that, we lose all the data. So what we end up is that b is equal to 0.0000000, and so on and so forth, all the way down to 0000. All the information within the number of b is actually lost. The computer can't store anything. In fact, b goes to 0. And obviously, if you add a then to b, b being 0, you're going to end back at a. So the answer to this is that a plus b is actually equal to a. So what the computer stores in 32 bits is exactly what it has stored for a. If you want me to write that down, that's 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, and lastly 1, 1, 1, 1. So that's the solution to a plus b. Now, in practical terms, this happens on your calculator as well as on a computer. The calculator and the computer are both machines. They only have a facility for storing a certain amount of accuracy. And in this case, because A is very big, B is very small, when it goes to add them, it actually doesn't pick up the difference that occurs when the addition happens. So it reports the answer back as being A. Okay, now let's look at exercise 2. Again, both numbers a and b are positive numbers, right, because they have 0 as their starting digit. If we look at the exponents and work them out in decimal using the calculator, the first value turns out to be 86 and the exponent for b turns out to be 83. So there's a difference, DIFF, between them of 86 minus 83, which turns out to be 3. The smaller one is b, so we're going to normalize b to have an exponent of 86. So b is going to turn out to be. So let's write it down in its form from the representation first. There's the significant. So it's 1.100, 1110, 0101, 1111, 0001, and 1111. And remember, that's by 2 to the power of 83. We want to rewrite it by 2 to the power of 86, so we can add it then. So what we're going to do is shift all the digits to the right by 3 places. So what you're going to end up as having is 0.00, so there's my 3 places. And then I start putting in the number. So the first 4 digits are these here. So, well, actually, I'm going to write them in, as the first digit. The first digit is a 1. Then the next 4 digits are these here. So it's 1, 0, 0, 1. The next 4 digits are 1, 1, 1, 1, 1, 0, 0. Sorry. The next 4 digits are 1, 0, 1, 1. The next 4 are 1, 1, 1, 0. And then the last 4 are 0, 0, 1, 1. And this is by 2 to the power of 86. Again, these 3 digits at the end, these 3 ones at the end, get lost and they're not stored by the computer. So this is my value for b, or this is my now rewriting b, and this is my a, which I'm going to add. So again, go back to the significant for a and rewrite that. It's 1.111, 0011, 1000, 4 zeros. I've left it very tight. 1100 and 0011. And again, that's by 2 to the power of 86. So now I'm in a position where I can add the 2, so I'm going to get a plus b. And a plus b is going to be by 2 to the power of 86. So when I add them, I have 1 and 1 is 2, so you put down 0, carry 1. 3 ones is 1, carry 1, and then there's a 1, 0. 0, 0, 0, 1, 0, carry 1, 1, carry 1, 0, carry 1, 0, carry 1, 1, 1. then it's 0, 0, 1, 0, carry 1, 1, carry 1, 0, carry 1, 1, 1. 1 and 1 is 2, naught, carry 1, naught, carry 1, naught, carry 1, and then it'll turn out to be naught, carry 1, so that'll be a 1 there. Sorry, a bit squashed. So that gives the answer for the addition. Now remember, the computer likes to store the number with a leading one, so it's 1 point. So again, I'm going to have to shift all the decimals to the right, and I'm going to get it's 1 point. And if I write the first as 3, so let me just group the first 3 together, so it's 1 point, the first 3 zeros, then again the next 4, 0, 1, 1, 0, then the next 4, 1, 0, 1, 0, then the next 4 is 0, 1, 1, 0, and then the next 4 is 0, 1, 0, 1, and then the last 4 is 0, 0, 1, 1. And again, this digit at the end just gets lost. So that's by 2 to the power of, and because I've moved it all to the right, this becomes 87. Now let me move this page up again just to give me a little bit more space. That should be plenty. So if you write down the 32-bit representation of a plus b, so the solution to the problem, 32 bits. Remember, it's a positive number, so 0 is the first bit. Now, the next 8 bits form the exponent, and there's a new exponent, it's 87. And the binary representation of 87, so you have to write it in 8-bit binary. Alright, just like it was before. So 8-bit binary, so it's 0, 1, 0, 1, 0, 1, 1, 1. So that's the 8-bit binary representation of the exponent. And then remember, if I put a box around this here, then the significand is taken from these 23 bits, so I just duplicate them in here. So it's 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, and sorry, the last one's squashed, 0, 0, 1, 1. So that's the 32-bit representation of a plus b.